Welcome to the discussion on process synchronization. In this session, we will explore the critical concepts of race conditions and critical sections. We will understand how multiple processes interact and the challenges that arise when they share resources. Get ready to dive into the world of concurrent programming. So, what exactly is process synchronization? Process synchronization is a mechanism that ensures coordinated execution of cooperating processes that share a logical address space to maintain data consistency. In simpler terms, it's about making sure that when multiple processes work together and share data, they do so in a way that keeps the data accurate and reliable. Why is process synchronization needed? Firstly, it prevents race conditions, which we'll discuss shortly. Secondly, it maintains data integrity, ensuring that the data remains correct. Lastly, it ensures deterministic program behavior, meaning the program produces consistent and predictable results every time it runs. Now let's talk about race conditions. A race condition occurs when multiple processes access and manipulate shared data concurrently, and the final result depends on the specific order in which the accesses take place. Imagine two runners racing. The outcome depends on who reaches the finish line first. Similarly, in programming, if multiple processes try to modify the same data at the same time, the final value of the data depends on which process finishes first, leading to unpredictable and potentially incorrect results. Here's an example of a race condition. We have a shared variable called counter initialized to 0. Process 1 increments the counter by 1 by reading the counter, adding 1 to it, and writing the new value back. Process 2 does the same thing concurrently. If both processes execute these operations at the same time, the final value of the counter might not be what we expect, leading to a race condition. Let's visualize a race condition with a step-by-step example. Imagine a memory location with a counter initialized to 0. Process 1 and Process 2 both want to increment this counter. First, Process 1 reads the counter, which is 0. Simultaneously, Process 2 also reads the counter, also getting 0. Then, Process 1 computes counter plus 1, resulting in 1. Similarly, Process 2 computes counter plus 1, also resulting in 1. Next, Process 1 writes the value 1 back to the counter. Finally, Process 2 writes the value 1 back to the counter, overwriting the previous value. The result is that the counter ends up with a value of 1, even though we expected it to be 2 because both processes increment it. This example demonstrates how a race condition can lead to incorrect results when multiple processes access shared data concurrently. Now let's discuss critical sections. A critical section is a segment of code where a process accesses shared resources that must not be accessed by other processes simultaneously to avoid race conditions. It's like a special room that only one process can enter at a time to prevent chaos. The problem we're trying to solve is that multiple processes need to access shared resources without interference from each other. The goal is to design a protocol that processes can use to cooperate and synchronize their actions, so that only one process is in the critical section at any given moment. To solve the critical section problem, any solution must meet 3 essential requirements. First, mutual exclusion. Only one process can execute in the critical section at any time. This ensures that there is no interference when processes access shared resources. Second, progress. If no process is in the critical section and some processes want to enter, only those not executing in their remainder section can participate in the decision of which will enter the critical section next. This prevents unnecessary delays. Third, bounded waiting. There must be a limit on the number of times other processes can enter their critical sections after a process has made a request to enter its critical section, and before that request is granted. This ensures that no process is indefinitely blocked from entering the critical section. Let's look at the structure of a process that includes a critical section. The process structure contains several sections. First, the entry section where the process requests permission to enter the critical section. Next, the critical section where the process accesses shared resources. After that, the exit section where the process releases the critical section, allowing other processes to enter. Finally, the remainder section where the process performs other tasks not related to the shared resources. In summary, a process repeatedly tries to enter its critical section, accesses shared resources, exits the critical section, and then performs other tasks before looping back to request access to the critical section again. Now, let's explore some common approaches to solving the critical section problem. First, software solutions employ algorithms that use shared variables to coordinate access to critical sections. A pro is that no hardware support is needed, but a con is that they can be complex to implement. Second, hardware solutions utilize special hardware instructions that provide atomic operations for synchronization. A pro is that they are simple and efficient, but a con is that they require specific hardware support. Third, mutex locks protect critical sections by requiring processes to acquire a lock before entry and release it upon exit. A pro is that they provide a straightforward concept, but a con is that they may cause busy waiting, where processes continuously check for the lock to become available. Fourth, semaphores are synchronization variables that control access to resources through atomic operations. A pro is that they are versatile for many scenarios, but a con is that they can lead to deadlocks if misused. Let's examine Peterson's solution, a classic software-based approach to solving the critical section problem. Peterson's solution uses shared variables, including a flag array and a turn variable, to coordinate access between two processes. The flag array indicates whether a process wants to enter its critical section, and the turn variable indicates which process has priority. In process I, it first sets flag I to true, indicating its intention to enter the critical section. Then it sets turn to J, giving priority to the other process. The process then waits in a while loop if the other process also wants to enter and has priority, waiting until either the other process doesn't want to enter or it no longer has priority. After exiting the critical section, it sets flag I to false. Peterson's solution guarantees mutual exclusion, progress, and bounded waiting, ensuring fair and safe access to shared resources. Let's summarize what we've covered. We discussed race conditions, which occur when multiple processes access shared data concurrently, leading to unpredictable results. We also defined critical sections as code segments where processes access shared resources that must be protected from concurrent access. Any solution to the critical section problem must satisfy the requirements of mutual exclusion, progress, and bounded waiting. We also explored various solutions, including software approaches like Peterson's solution and hardware-supported mechanisms like mutex locks and semaphores. Up next, we'll delve into more advanced topics such as semaphores, monitors, deadlocks, and classic synchronization problems. Thank you for joining me on this journey into process synchronization. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.